Hello everyone. In this video, we introduce the notion of matrices and matrix operations. The theory of matrices is a valuable tool in science and engineering. The use of matrices provide a way of representing systems of linear equations that can be handled by computers, which are well suited for manipulating arrays of numerical information. But more than being notational tools, matrices can be viewed as mathematical objects in their own right, and there is a rich and important theory associated with them that has a multitude of practical applications. So what is a matrix? An m by n matrix, or a matrix of size mn, is a rectangular array of mn numbers arranged in n horizontal rows and n vertical columns. For ease of notation, we usually use this symbol to represent a matrix. Here, the A sub ij, which is the number in the ith row and jth column, is called the ij element or the ij entry of matrix A. In the array, the subarray whose elements have a fixed first subscript is called the ith row of the matrix. Similarly, the subarray whose elements have a fixed second subscript is called the jth column. A matrix of size 1 by n or n by 1 will be simply called an n vector. If the matrix has the same number of rows as its columns, say n, then we call the matrix a square matrix of size n. In this case, the matrix has a well-defined diagonal entries, and the entries are called the diagonal entries of the matrix. Let's look at some examples. For our first example, we have A, which is a 4 by 3 matrix. The 2-1 entry, which is the entry in the second row, first column, is negative 1. The 3-2 entry, which is the entry in the third row, second column, is 14. And the entry 822, which is the entry in the second row, second column, is 0. An important example of a matrix is the matrix I sub n, which is a square matrix of size n. Its entries delta sub ij satisfy the following rule. The value is 1 if I equals j and 0 otherwise. In other words, In is the square matrix whose entries along the diagonal are all 1 and 0 elsewhere. So here we see the matrices I sub 1, I sub 2, and I sub 3. And you can guess the shapes of I sub 4, I sub 5, and so on. The matrix I sub n is called the n by n identity matrix. The m by n matrix, whose entries are all 0, is called the zero matrix, and we shall denote it by 0 sub mn. Matrix of size n that satisfies A sub ij equals 0 whenever I is not equal to j is called a diagonal matrix. a matrix of size n that satisfies A sub ij equals 0 whenever I is greater than j is called an upper triangular matrix. So this tells us that in an upper triangular matrix, the entries below the diagonal are all 0. And we can similarly define the notion of a lower triangular matrix, wherein the entries above the diagonal are all 0. So here are some examples. This is a diagonal matrix. This is an upper triangular matrix. And this is an example of a lower triangular matrix. Like numbers, matrices can be compared, and we say that matrices A and B are equal if they have the same size and their respective entries are the same. In other words, if A is m by n, then B should be m by n as well, and the respective entries should coincide. So to illustrate, consider matrices A and B as shown. So both A and B have size 2, and we say that A and B are equal if and only if 1 equals x, 2 equals y, 2 equals z, and negative 3 equals w. Using the notion of matrix equality, systems of linear equations can be translated in the language of matrices. For instance, this system, as shown, translates into this matrix equality. Another example is what is shown for this system is a system of 4 equations, and we can view it as an equality of 2 4 vectors. We can also view it as an equality of 2 2 by 2 matrices, depending on how we position the these entries. This example tells us that there are various ways of writing a system of equations as a matrix equality. Sometimes the choice of representation would make or break the solution. It could simplify the problem, or it could turn the problem into a more complicated one. It's important to remember to understand how best to represent a system of linear equations as a matrix equality. Let's now proceed to the arithmetic of matrices. Just like usual numbers, we can perform addition and multiplication with matrices, but one needs to be cautious when performing these operations. For instance, to add two matrices A and B, first they must have the same size. Say they are both m by n. Okay, so in this case, the sum A plus B is well defined, and we define it to be the matrix whose entries E sub ij are obtained by adding the respective entries E sub ij of A and B sub ij of B. Again, we should remember that addition is only possible when the matrix summands have the same size. To illustrate, consider these matrices A and B. So this is A, this is B. Both are 2 by 3 matrices. So they have the same size. So we can compute the sum of these matrices. And the sum is as shown. It is also 2 by 3, whose entries are simply obtained by getting respective sums. So this is the sum of these two matrices. We can also write a system of linear equations as a matrix equality involving a matrix sum. Okay. Earlier, we saw this representation. Okay. This system is represented by a matrix equality, but actually we can do more. In this equation, the left-hand side can actually be expressed as a matrix sum. Okay. As you can see, we can split it into a sum of two vectors. Another operation we can perform with matrices is the so-called scalar multiplication. This is something familiar to us from elementary calculus or elementary physics. Okay? For an m by n matrix A, and scalar C, the matrix CA, or the scalar multiple of A by C, is defined to be the matrix obtained by multiplying each entry of A by C. Okay. So, for instance, we call the matrix I sub n, okay, the m by n identity matrix. If we multiply I sub n by a scalar C, then we obtain a matrix of this shape, okay, which is a diagonal matrix, and such a matrix is called a scalar matrix. So for a more concrete example, look at this matrix operation. So here we have a 3 by 2 matrix being multiplied by scalar 3. And as we can see, the result is a 3 by 2 matrix whose entries are 6, 0, 3, 15, negative 3, negative 9, each obtained by taking the product of each entry by 3. Earlier, we saw that this system of linear equations can be expressed as a matrix equality and in turn into a matrix equality involving a sum. But in fact, we can do more. So on the left-hand side, you can observe that the first summand, the entries contain x1, and the second term, second summand, both entries contain x2 as a factor. So we can actually write each of these vectors as scalar multiples of matrices. Indeed, if you take out x1 of the first term and x2 of the second term, the left-hand side can be written in this manner.